Okay, confidence interval for population proportions. And I'll just emphasize, so remember there's a textbook in here. So if you want to pull that up, you can always scan over. You'll see formulas, you'll see descriptions in the printed page. Sometimes that is helpful. Um, Sometimes it's not, but it's there for you. Uh, this is where I get the in-class learning activity. Again, you have access to that as well, and it's maybe helpful, especially as you're reviewing, to go back. And then now the homework is right in here. And again, I've got it broken down by section. So if I do it right, which I haven't always, I'm finding a few questions that I got in the wrong place, but uh, hopefully this next one I'll get it all right. Uh, as we go through it, you'll be able to work all of those, all the homework problems in there. Now, this one is the longest section, um, but it was also the first section of questions in the homework. So um, maybe my colleagues that invented this or created this actually taught it backwards. So um, at least it seems that way from how the homework is. Okay, so now this is confidence intervals for population proportions. Um, let's take some of the mystery out of that. What does the word proportion mean? What would be a substitute word that you could use, that we use all the time? What is a proportion? A what? A piece, exactly. Good. It's a piece of something, or a percentage is how. So we use percentages to. So yeah, piece, a fraction. Excellent. Um, so this is going to be, and proportions also come from fractions. Um, so since we're dealing with probability distributions, the fraction is always going to be less than one, greater than zero. So just think, uh, I just replace it with the word percentage. Oh, now I understand what we're talking about. Proportions, I don't know. Okay. So that's where I put relative frequency, percent, and this is how we are going to deal with binomial stuff. Okay. Um, and as long as the binomial stuff is relatively close to being normal, that's what we need here. Okay. Um, so the population proportion, the probability of success in a single trial is P. So kind of just remembering what we did. This was in chapter 5. Chapter 5. Uh, we're going to get the point estimate for P, and that's simply the percentage. So again, we're looking for the point estimate of P in the population. What we're going to do is we're going to be able to calculate what we call P hat from a sample. Okay, so this is how we're going to do it. So, and they call this little thing on it a hat. I guess like I've got a hat on too. So right, you just put a hat on. So that's a sample proportion. X is the number of successes in the sample. N is the sample size, and the proportion of failures is always going to be Q hat, which is 1 minus P hat. Okay, and so don't get too much into the symbols. It really is just the same thing we were doing before, but since we're not working with the population, we come up with some symbols that say these are from samples. And what we're trying to get is what is the population proportion? And it's unknown, but we can get through by using the sample. So here's an example in a survey of 540 US adults. 378 said they planned on traveling this summer. Find a point estimate for the population proportion of US adults who plan on traveling this summer. That I had more to it. So how would we do that? I'm going to do it this way, but what you're going to see is we actually don't even need to do this because Numworks has it built into the calculator. But just so you see what it's doing, it's going to take the sample size and divide it into the portion, the piece of the sample that said they would travel. Okay, and I'll show you that one while we're just working on this. So we're going to come back, and now instead of doing one mean, we're going to do one proportion. And notice it's going to use the z interval. So when we're doing one proportion, It will be a z-interval thing. Here, instead of telling what the proportion is, we tell the number of x, which is oftentimes what we're given because that comes from the sample, 378. That's why I like this calculator. If you use a TI-84, you actually have to calculate it and put in the percentage. This is going to do that for us. I think they were thinking ahead. What was it, 378? Yeah, 378. Sample size, 500, right? Or 540. Good thing I checked. Confidence interval, they want, well, they just want the point estimate. I thought I changed this. Let's do a 90%. It doesn't say, we can do whatever we want. And what we'll see is it gives us p hat, which is the point estimate. It's 70%. You also could have just taken 378 divided by 540 and gotten 0.7. But if you put it all in here, you'll get it here, you get your critical values, and you'll also get your margin of error. So the margin of error is about 3%, right? 3.2%. So that's everything we're dealing with. The proportions is all percentages. Okay, so you can think of them as percentages or as decimals. And again, if you actually needed that confidence interval, it's right here. Bless you. So 66.7% to 73.2%, that's what the population proportion should be, right? Or 95% confident, 90% confident. You want to be 95%, then we go to there, okay? And again, that's why I like this, is we can rather quickly see what different confidence intervals are. And so, like if you're planning a research project, you might want to, because you have some freedom in saying, should I do a 90% or a 95%? You could look here, oh, a 95%, it's got to go there. Which one should I use? But you've got these values easy to look at, okay? Looking just like the other stuff, right? Not much different, just we're dealing with percentages, okay? So said I'd get done in about 10 minutes. I might be 15. Okay, so this is the formula for calculating the margin of error. You can see it's p hat times q hat over n. Remember the standard deviation was npq, square root of that. So it's kind of in there, but then you're having to divide. And again, if you take some advanced statistics classes, you will probably get into the theory behind this and where those formulas come from. Most of us are just happy to get their answers and see how that relates to the research we're doing or to the question we're trying to answer. Okay, and again, this is all going to be built into the NumWorks calculator. So you will not be asked to individually use it, except we're going to solve this for n because there are a couple questions we're going to want to calculate what is the sample size needed. Again, why is that important? Because it's hard to go back out into the field if you get your results. Oh, we need more sample. Oftentimes you can't get it because remember, you got randomization. It's a whole process. So you want to get your whole sample when you go out to do your research. You want to collect at one time. So we'll talk about that in just a moment. There is also a thing, let's see. Go back. We can really only use this if the sample size times p hat that we come up with is greater than or equal to 5, or the sample size times q hat. Well, both of these have to be true, have to be greater than 5. So if your sample size is small enough, like, and it just depends on your proportions, right? If one of these are less than 5, then this is not going to work. Okay, so occasionally you have to, get your estimate and then see if the sample size times that is going to be greater than 5. Again, you can kind of do this. You get an estimate of what P is, and then plug in some values for N to see what sample size you're going to need so that you're at least bigger than 5, because that makes it normally distributed. And then if we want to get the critical values for Z, we don't use the tables but we go back and use the normal distribution. That's just like the first thing we did. Okay, the margin of error. Again, this is the formula, one that we won't be using, but you could kind of see it's taking that critical value times approximately the standard deviation, and we get a plus and a minus on the error, so we get a proportion. And again, the one without the hat in the middle, that's the population. The ones with the hat, those are from the sample. Remember, since we're pulling a sample, our mean, our proportion in the sample is likely to be slightly different with each individual sample taken. But we get a confidence interval of where the population portion should be. Oh, this is where I should have moved this up further. So we've actually already done this one. So this is the 540 adults, 378 said that they plan on traveling, construct a 95% confidence interval. Notice I really have everything I need to input right here. I just need to know what the sample size was, how many said yes, or, and then what is the confidence interval they need. And when I go to input, that is all that I input. And that will give me my answers. So in this way, it's maybe even a little easier than the previous two. Here's, again, one, we looked at something like this before. The figure below is from a survey of 800 U.S. adults. Construct a 99% confidence interval for the population proportion of U.S. adults who prefer to get their news from television. So television is here. So for the sample, that's 35%. Again, this is where it's a little difficult, but not too difficult, because our NumWorks calculator wants us to give X. It doesn't want us to input the percentage. So how are we going to figure out what is 35% of 800? How do we calculate 35% of 800? Multiply 0.35 times 800. The cool part is, just like we've done with some of the other things, if I go here, we can just put 800 times 0.35 right in here, and it will calculate that for us. And then the sample size was 800. So it's not a big deal, but you have to remember, you don't put in the 0.35. Other calculators you would, but we have to put the X value. So when they give you the percentage, it's actually a little bit of an extra step, that multiplication. They want a 99% confidence interval. So we do a 0.99, and we get everything. So our sampling proportion is 35%, which we knew that, right? So we, be nice if we could come here and put it in, but we can't. So critical values, standard error. So the margin of error is the important part. So that's our population proportion is going to be about 35% plus or minus 4%, right? And again, we go one more step. All we're getting, we got our confidence interval here, about 30.6 or 30.7 to 39.3% is what the population would be at a 99. And again, we've got it here as well. And just depends on, in the homework, how do they want it. But these are very straightforward. all we put in is the X value, the sample size, and the confidence interval, and the NumWorks calculator handles all the formulas for us. But at the end, we have to remember what we're getting is a point estimate for the population proportion and an interval where we're 99% confident that it's the population proportions in there. And that's how they do things like when they're when we have elections. And especially as they can call them before all the votes are in, because they can make this confidence interval and says, even though there's still, sometimes they can do it early on, there's still 60% of the vote that needs to come in, they might be able to call it because they can say the other person doesn't have a chance of getting enough. So they use statistical tools similar to this to call election races. Now this is the last part we're going to do, and this is the part where we do have to use some formulas. There's about 3 questions at the end. Remember, all you have to do is 90%. If you really wanted to skip this, you could skip this and still get full credit. I just be transparent here. But if you want to see how to make a sample size or how to determine a sample size, given a C confidence level and a margin of error, the minimum sample size N needed to estimate P. Okay, so this is the equation we start with, right? So you could plug in everything and then do algebra, but it'd be nice if somebody did the algebra for us, and they did. So this is the formula when you go to do those problems that you're going to need. Okay. So you'll need your P hat, your Q hat is 1 minus P hat. You'll have to find your Z critical value. And the margin of error usually is given. They'll say plus or minus 3% or plus or minus 5%. And then that tells you what sample size you need. Okay. Always round it up to the next number, because if you need 86.3, you're actually going to need 84 to make everything work. And if the proportions are not given, this is kind of a cool thing. What you do is you start with a 50-50, and you'll get a good estimate. So you might say, I won't know that until I collect some data. So a lot of times what you have to do is just start here, and you'll see you'll get close enough. This will give a larger sample size than you need, but at least you won't have to go back and take any more samples. Okay, so I put this little guy down here because that's all we're going to use. You are running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3%. That is your margin of error that they're giving you right there of the true population. Find the minimum sample size needed when no preliminary estimate is available. Okay. If it's not available, we use P hat at 0.5, which makes Q hat be 0.5 as well. Okay. And then we're going to see, they'll give us some, and then it'll come up different. And so this calculation, remember the 95%? If you didn't, we'll do that real quick. We can get that by going back to distributions. And we can use the normal distribution, standard normal. We get the middle, we want the middle, what's the percent? 95%. So we put in 0.95. 1.96. So we'll round up the 5 to a 6. We'll just use the 2 decimal places, 1.96. So we've just calculated our Z critical is 1.96. And so we just use this formula. It's going to be 0.5 times 0.5 times 1.96 divided by the error, which they gave us was 3%. So 3% as a decimal is 0.03, and then we square that. Okay, so we just follow the formula, plug things in, and then we can do all those calculations from the regular calculator. 0.5 times 0.5 times parentheses 1.96 divided by 0.03. Arrow out a little bit, put a parentheses, and then we want to square that. There's a little x squared here. Put that, that'll square it. And that will tell us we need 1,067, but 0.1, we got to round it up to 1,068. Our answer is 1,068 sample size. And you might have thought going out and getting 300 would be enough, but you'd be way off, right? Your margin of error is going to be like 5 or 6% or something. You know, it's going to be much bigger. So that's why we do this. And what I want to show you is this is not too hard to do. We'll do the next one. Okay, so 0.5 and 0.5. This is the same thing, but they give us a preliminary estimate. Maybe this was from the last polls or something, that p hat is 31%. So if p hat is 31, what would q hat be? Remember, they have to add to 100%. Yes, 1 minus 0.31, which is going to give us 0.69. And since they want a 95% confidence interval, again, we could go back to the normal distribution, or just remember that the z critical for 95% is always 1.96. And again, when you're doing statistics, usually they'll stick with the same amount, so you don't have to keep looking those up. So hopefully I can remember the formula. N is going to be equal to p hat, which is 0.31, times q hat, which is 0.69, times 1.96. We still want the 3%, so we do 0.03 squared. And now when we put all of that in, again, we could just come back up here, I think, and just say enter it, and then change these percentages. So instead of 0.5, we're going to do 0.31. And instead of 0.5, we're going to do 0.69. We get 913. So 50-50 is actually going to give us the largest sample size needed. So that's why we can always use it if we don't know. But if we do know an estimate, we might be able to save ourselves some work. Okay. So actually, even this one, you want to round it up, even if it's 0.02, you really want to go to 914. And again, there's, I think, 3 questions at the end that ask you to calculate the sample size. If you want to skip it, you can, but it's not that hard. Just use this formula. Okay, I told you, oh, well, it was 25 minutes, but it wasn't a half hour, was it? Okay.